Hello everyone, today I'm presenting my work on federated multi-trajectory GNNs under data limitations for baby brain connectivity forecasting. This work has been done at Basira Lab by myself and supervised by Dr. Islam Regic. So let's start with the problem we want to solve. Given a baseline morphological connectome at time point t0, we want to forecast the brain's trajectory evolution for both the morphological and the functional connectome over time. There are several studies related to brain evolution predictions. The first work involves a variety of bidirectional regressors to get similarity scores. Then in the following study, the authors propose another selection framework by assessing all infinite pathways across them. Moreover, the next paper proposes the use of GCNs to learn adversarial brain graph embedding used for a selection strategy. Another work proposes EvoGraphNet, which cascades time-dependent graph-generative adversarial networks for the trajectory prediction. And finally, we have recurrent brain graph mapper, which follows the same idea of cascading but with a series of recurrent neural networks instead. Despite their significant contributions in the field, they do have some limitations. First, they require a large training dataset for satisfactory performance, which is usually not feasible when dealing with medical data because they are quite constrained and sensitive. Moreover, all of the above works focus on a unit trajectory prediction, while a multi-trajectory generalization could allow us to focus across multiple imaging techniques, giving diverse insights into brain development. The first work that tried to address these issues is the following. The authors introduce a novel framework for fusion learning in the context of multi-trajectory evolution with the help of a teacher-student paradigm. However, the teacher-student paradigm has its limitations. First, it's computationally expensive, since it involves two separate networks. Also, due to the heavy reliance of the student network to the teacher, any bias or noise introduced by the teacher is further amplified. Finally, it utilizes simulated data to increase the training dataset, which is not optimal since they are not fully realistic. So we now move to our proposed framework, where we suggest the use of a federated learning paradigm. In such a setting, we have the individual hospitals with their own local training datasets, and the aim is to train them collaboratively. Hence, after the hospitals perform their local training, we share the model updates with a central server, which then aggregates these updates and distributes them back to the hospitals. In that way, we can facilitate the collaboration of many independent hospitals and thus take advantage of the increasing data they introduce, while still preserving data privacy. Moreover, the use of multiple hospitals allow us to train on diverse datasets, which can increase generalization. Now, moving to the model of each hospital individually. Each local hospital has its own dataset with subjects. However, since we are dealing with longitudinal datasets, it is expected that some of the subjects will have missing data at some time points. Our only prerequisite is that they all have full availability at the baseline time point. So we need to find an efficient way to deal with the missing data. So we propose the use of a KNN-based imputation technique. We take advantage of the full availability at the baseline time point to calculate the similarity scores across subjects, which we then use to impute the missing values at the subsequent time points. We can now move to the core network for multi-trajectory evolution prediction. The input is a simple baseline brain graph at the morphological connectome that first gets vectorized and then passes through our encoder to get its latent representation. Then we have a set of decoders for each separate imaging technique used to forecast the brain trajectory across time points. Our objective function combines the output loss and our regularizer loss, which we'll discuss in more detail shortly. Our output loss includes the standard wall loss with an additional term to capture the topological properties of the brain graphs. Having said that, let's now introduce our regularizer, which concerns the modules surrounded by this red border. This module is located at the start of our network. The input of this module is the vectorized baseline brain graphs of the morphological connectome, while the outputs are the predicted brain graphs of our network at time point t0 in the relevant imaging modalities. As you can see, this module does not seem to depend on the temporal nature of our data, since the input and output share the same time point. Hence, we propose using all available longitudinal brain graphs for its training so we can maximize data utilization. To evaluate a framework, we use longitudinal multimodal infant brain connectomes. In particular, we have just 25 subjects, and for each subject, we have both functional and morphological connectomes. We group our data in three distinct time groupings, and we use fourfold cross-validation. we perform experiments in both an IID and a non-IID setting. We have two distinct evaluation metrics, with our primary being the standard MA graph and the secondary being a measure of node strength to measure the topological similarities. Our benchmark methods include the standard no federation version with no sharing of knowledge and the simple federation framework without any of the auxiliary additions we propose. And finally, we have of course our proposed framework. Here, we can see the MA graph results across hospitals first for the IID setting and second for the non-IID setting. In both cases, it is clear to see that our method significantly outperforms the alternatives across almost all scenarios. For more experimental numerical results, you can also check our paper. Moreover, as an additional form of validation, we also present visual comparisons between our framework's predictions against their real counterparts in both the morphological and the functional connectome. As we can see, the predictions are quite similar across modalities and time points. In conclusion, in this work, we present the first graph multi-trajectory framework that leverages federation for forecasting infant brain evolution trajectory from a single modality graph. As our key contributions, we first propose the incorporation of a topology loss term to preserve the topological features of brain graphs. Moreover, we introduce a KNN-based imputation technique to effectively address the issue of data scarcity in longitudinal graph datasets. Finally, we propose a novel auxiliary regularizer to enhance data utilization in a limited data environment. In our future work, we can consider the whole history of graph predictions to make predictions at the current time point despite relying solely on the previous time points. And finally, we would also like to explore dynamic imputation approaches to complete training multi-trajectories in an end-to-end learnable manner. For more, please visit us at basira-lab.com.